Hi everyone, we are from Session 3, Group 1. Today, our group will present our thermofluid assignment. The topic is internal flow analysis, and the object we choose is water pumping system. We will look at how centrifugal pump will check out the fluid properties and walk through the engineering calculations. Let's move on to the next slide. Our team consists of 4 members. First is Gan, which is my name. Second is Putra. Third is Izme. And last is Azim. Introduction. For this project, we choose the ground force radical multi-stage centrifugal pump system. First, what is internal force? Internal force is fluid flowing inside a completely enclosed boundary like water moving toward a pipe. As it moves, the friction from the pipe will create a boundary layer that grow inward until the flow becomes fully steady and fully developed. Here is the quick spec for our pump. First is size and weight. It is compact, measuring 350 by 270 by 315 millimeter and weight about 15 kilogram. Second, power and performance. It runs on a rate of power of 0.5 kilowatt, pushing a max flow rate of 3.0 cubic meter per hour up to max head of 46 meter. Third is its price. It costs around 1,800 ringgit Malaysia to 2,200 ringgit Malaysia in market. The last one is called job. It converts mechanical energy into hydraulic energy to boost the fluid pressure. For the next slide, we will analyze this system using the Bernoulli and energy equation. Next, let's talk about mechanics of operation. Let's start with system working principle. First, the source. Water start at ground level storage tanks supplied by a municipal main line. Second, the suction. The pump draw water toward a short, straight 25 mm suction pipe. We keep it short on purpose to minimize head loss and prevent cavitations. The third, the boost. The water enter the pump where rotating impeller add kinetic energy and the casing convert it into pressure. 4. The delivery. The pressurized water travel out the delivery pipe network all the way to overhead road tanks. 5. The user. Finally, the gravity feed the water down to the household tap and shower at the reliable pressure. Next, we move to the working fluid. Our working fluid is water because it's cheap, stable, and reliable in our real life. Taking our data at the standard room temperature of 20 degrees Celsius, here are the properties we use for our map. First, density, which is 998.2 kilogram per meter square. Second, dynamic viscosity, 1.002 times 10 to negative 3 Pascal second. Third, kinematic viscosity, 1.004 times 10 to negative 6. Next, we move to the internal flow analysis. To find the Reynolds number, we need to use this formula. Using our flow rate value and the pipe diameter value, we first get its area, which is 4.909 times 10 to negative 4 meter square. This giving us a flow velocity of 1.697 meters per second. By plugging those values into the formula, we get the Reynolds number, which is 42,250. Is way more over than 4,000. Way more over than 4,000. The flow turbulent, which is the water is mixing aggressively with a flat velocity profile across to the pipe. For the next contents, I pass to the Azim.
Next, I will explain the entering reagent and friction factor. When water enters the pipe, the boundary layer develops until the flow becomes fully developed. Using the turbulent flow equation, the entering length is calculated as 0.63 meters. For the friction factor, we use the Swammerdgen equation, which gives a value of approximately 0.022 for our PVC pipe. This value is also consistent with the Moody Chart, confirming the pipe has flow friction due to its smooth surface. Next is the head loss and pumping water. The major head loss is 2.58 meters, while the minor head loss from waft and elbows is 0.91 meters. Therefore, the total head loss is 3.49 meters. Adding the started head of 10 meters, give a total dynamic head of 13.49 meters. Finally, the required pump input power is 169.4 watts or approximately 0.17 kilowatts, which is sufficient for this water pumping system. Thank you. Next, I will pass to Putra.
Hi, my name is Putra Nofaris Ibn Fairuz. Now, my part is a problem and statements. The first problem is a water leak. They happen at the mechanical seal between the pump shaft and the casing. It is a leak caused by seal wear, incorrect installation or high operation pressure. Or when the seal is damaged, water can leak out through the rotation shaft. Now, the second problem is low discharge pressure. This is across the pump outlets. The main causes are trapped in the traction line, corrugated pipes, or impeller. Because of this problem, the pump cannot transfer enough energy to the water, so the discharge pressure becomes low. The third problem is self-vibration and noise. This can happen throughout the pump and motor assembly. It is mainly caused by a cavitation, bearing wear, or shaft measurements. When vapor bubbles form and collapse inside the pump, they create a vibration and noise, which can damage the pump over time. Now, in conclusion, there's a three problem can reduce the pump performance and efficiency. Therefore, regular inspection and proper maintenance are important to keep the pump operation safely and efficient. Thank you. Now, I will pass my friend Ismail.
So, there are 4 suggestions to improve our model. First, we can add tiny internal caps and wear rings directly into the geometry. This helps us to accurately capture volumetric leakage and efficiency drops. Secondly, we can optimize the diffuser channels. By refining the stationary return guide vanes between all 5 stages, we can prevent flow separation and pressure losses. Next, we can replace the steady state snapshots to transient sliding mesh models, and it will let us capture real world pressure pulsations and rotor stator interactions. Lastly, we must verify the seal cavity flow, including the rear hub chamber, in our simulation. This ensures adequate fluid circulation and cooling around the AQQ mechanical seal. Thank you. Now I would like to pass it to my friend Gan.
Hello everyone, my name is Gan. Let me make a conclude for our project. In conclusion, this project shows why analysis internal flow is so important for a water pumping system in our life. By looking at flow behavior, head loss, frictions, and pump efficiency, we learn how to optimize the system. This helps us lower energy consumption and avoid future maintenance issues. Ultimately, keeping a water pumping system reliable and efficient comes down to 2 main things. First, choosing a right pump. Second is keeping up with regular maintenance. Thank you for your listens. I'm happy to take any questions. And here I will give a video to explain about internal flow, about pumping system. Thank you.
Centrifugal pumps are the most preferred pumping devices in the hydraulic world. In this video, we will have a conceptual overview of working of centrifugal pumps. At the heart of the system lies the impeller. It has got a series of curved vanes fitted inside shroud plates. The impeller is always immersed in water. When the impeller is made to rotate, it makes the fluids surrounding it also rotate. This imparts centrifugal force to water particles, and the water moves radially out. Since rotational mechanical energy is transferred to the fluid, at discharge sides of impeller, both pressure and kinetic energy of water will rise. At suction side, water is getting displaced, so a negative pressure will be induced at I. Such low pressure helps in sucking fresh water stream into the system again, and this process continues. This is the reason why priming is important for centrifugal pumps. If no water is present initially, the negative pressure developed by rotating air at I of impeller will be negligibly small to suck fresh stream of water. Impeller is fitted inside a casing, so the water moving out will be collected inside it and will move in the same direction of rotation of impeller, to the discharge nozzle. Here you can note one specialty of casing. It has got increasing area along the flow direction. Such increasing area will help in accommodating newly added water stream and will also help in reducing exit flow velocity. Reduction in flow velocity will result in increase in static pressure, which is required to overcome resistance of pumping system. Here you can see more details of vanes inside impeller. They are backward curved vanes with state-of-the-art eye configuration. This vane is extracted from a Kirloskar pump model. If pressure at suction side of impeller goes below vapor pressure of water, a dangerous phenomenon could happen. Water will start to boil, forming vapor bubbles and spoil impeller materials over time. This phenomenon is known as cavitation. More the suction head, lesser should be the pressure at suction side to lift water. This fact puts a limit to maximum suction head a pump can have. Careful pump selection is required to avoid problem of cavitation. Current impeller type is enclosed. Semi-open and open impellers are also in use depending upon application. If the working fluid is cloggy in nature, it is preferred to use open kind of impeller, but they are slightly less efficient. Mechanical design of centrifugal pump is always challenging. A shaft is used to connect between the impeller and motor. Since water pressure inside casing is huge, a proper sealing arrangement is imperative in arresting water leakage through shaft casing clearance. Mechanical seal or stuffing box-based mechanism is used for this purpose. Impeller is mounted on bearings, but at suction side of impeller, it is not advisable to fit a bearing since it will block the flow. So bearings have to be fitted at the other end. This means impeller is mounted like a cantilever. For high flow rate pumps, a bearing housing with cooling oil is necessary for improving life of bearings. We thank Kirloskar Brothers for their technical support and creation of this video.